Hi, Assalamualaikum warahmatullahi wabarakatuh. First of all, highest appreciation to our Madam Rafidah binti Ali to being our lecturer. And today we will present about case studies, which is the linear programming. And first and foremost, my name is Muhammad Zahiruddin Zulkifli, and I will present about introduction. Linear programming is a method that we use to find the best outcome, the minimum or maximum, in a mathematical model, which is it is a technique to solve a problem, which is it involve the first one, objective function, the second one, set of constraint, and the third one, non-negativity, which is the number must not be negative. So when there are only two variables, we can solve the linear programming problems by drawing a graph. With this technique, we can help to find the best solution for our problem. So with that, it makes us confirm and more confident to use the solution to solve a problem. In this project, we have discussed about case studies that involving two resources, which is the labor and the wood. The company produced tables and chairs, and the company wants to make the most profit. So to solve this problem, the first step is we write the equation, which is we want to maximize or minimize, and then we make a constraint, which is the limitation, and to make sure our number is positive. The second one, we draw a graph using the constraint, and the third one, we find the feasible region, and the fourth one, use the interception method to find the key points, and the fifth one, the last one, calculate which point give the highest profit. So with that, with this linear programming method, we can solve the problem. And with this method too, we can use as well to solve a minimum problem.
As you can see in the slide, this is our case study, our first case study question, which is about linear programming by graph for maximum problem. So you can see at the next slide how we solve this case study using linear programming by graph for maximum problem. Now I will solve the case study question, which is by using linear programming by graph for maximum problem. So now I will show you step by step from the step 1 until the last step how to do the calculation. So for the step 1, which is formulate the LP problem. So we begin by defining our linear programming problem to maximize profit for a furniture company. The decision variables are straightforward, which is X represent the number of tables produced and Y represent the number of chairs produced. Our objective is to maximize profit, which is calculated using the profit per unit. Each table contributes $6 and each chair contributes $8. This gives us the objective function become Z equal to 6x plus 8y. So next we incorporate the constraint. The wood constraint limit us to 300 units of wood, with each table consuming 30 units and each chair consuming 20 units, leading to the inequality 30x plus 20y is less than or equal to 300. The labor constraint allows 110 hours of work, where each table requires 5 hours and each chair requires 10 hours, resulting in 5x plus 10y less than or equal to 110. Finally, we include the non-negativity constraint, which is x is greater or equal to 0 and y is greater or equal to 0, ensuring our solution are practical. So that is all from the step 1. We're gonna go to the step 2, which is solve the constraint equation for intercept. So to graph this constraint, we first convert this inequality into an equation and solve for their intercept. Starting with the word constraint equation, which is 30x plus 20y equal to 300. We find the x-intercept by setting y equal to 0. Solving 30x equal to 300 gives x equal to 10. So the x-intercept is 10, 0. For the y-intercept, we setting the x equal to 0. Solving the 20y equal to 300 to get y equal to 15. Gives us the point 0, 15. Moving to the level constraint, which is 5x plus 10y equal to 110. We repeat the process again, which is setting y equal to 0, become 5s equal to 110. So the s is equal to 22, and the x-intercept is 22, 0. Setting the s equal to 0 gives 10y equal to 110. So the y equal to 11, and the y-intercept is 0, 11. This intercept 0, 10, 0, 0, 15 for the word and 20, 0, 0, 11 for the label are the foundation for plotting our graph. Okay, now we go to the step 3, which is draw the graph and identify the feasible region. With our intercept calculated, we proceed to the plot the constraint on a graph where the x-axis represent tables and the y-axis represent chat. We draw the word constraint line by connecting 10, 0 and 0, 15, and the label constraint line by connecting 22, 0 and 0, 11. To determine which side of the line is valid, we test the origin point 0, 0. Substituting the 0, 0 into the word constraint become 30, 0 plus 20, 0 equal to 0, which is less than or equal to 300. Holds true. So we shaded the region toward the origin for this constraint. Similarly, for the label, 5, 0 plus 10, 0 equal to 0, which is less than or equal to 110 is valid. So we shade toward the origin again. The feasible region where our constraint overlap form a polygon bounded by 4 corner points, which is 0, 0, 0, 11, the intersection point of the two lines, which we soon calculated as 4, 9 and 10, 0. This shaded contain all possible production plan that satisfy our limitation.
Hi, my name is Patricia Adriana. I will now continue the presentation with the step 4, which is interception method. It's also known as the elimination method. In this step, our main goal is to find the exact point where the two lines meet. This is shown by the red circle on the graph. To solve this, we are given two equations, 30x plus 20y equal 300 and 5x plus 10y equal 110. Our goal is to find the point where these two lines intersect, which means we need to find the value of x and y that satisfy for both equations. First, we try to eliminate one of the variables by making the y terms the same. We do this by multiplying the second equation by 2. So, 2 multiply in the bracket 5x plus 10y equal 110. So, the answer is 10x plus 20y equal 220. So, now we subtract this new equation from the first one. So, it will give us 30x plus 20y minus 10x plus 20y, so equal 300 minus 220. So when we simplify, we are left with 20x equal 80. So to solving for the x, we divide for both sides by 20, and for the x we get 4. Next, We substitute x equal 4 into one of the original equations to find the value of y. Using the second equation, 5x plus 10y equal 110, we substitute and get 5 in the bracket 4 plus 10y equal 110. This becomes 20 plus 10y equal 120. So subtracting 20 from the both sides gives us 10y equal 90. And dividing by 10 gives y equal 9. So the final answer is x equal 4 and y equal 9. This means the two lines intersect at a point is 4 and 9. On the graph, this point is shown with a red circle and it represents the exact location where both equations are true at the same time. Next, proceed with step 5, choosing the maximum value. In this problem, we are trying to find the maximum value of the objective z equals 6 plus 6x plus 8y by testing a specific corner point of this region. The corner point we check are 0 and 11, 4 and 9, 10 and 0, and 0 and 0. For each point, we plug the x and value into the equation to calculate z. At 0 and 11, z equal 6 multiplied 0 plus 8 multiplied 11 and equal 88. At 4 and 9 point, z equal 6 multiplied 4 plus 8 multiplied 9, so the answer is 96. At 10 and 0 point, z equal 6 multiplied 10 plus 8 multiplied 0 equal to 60. At 0 and 0 point, z equals 6 multiplied 0 plus 8 multiplied 0, the equal is 0. So the higher value of z is 96, which occurs at the point 4 and 9. This means 4 and 9 is the best solution because it gives the maximum result for the function or objective.
I'll be continue presenting a linear programming minimum case study involving Crunchy by Sendirian Berhad, a snack food manufacturing company. So the company produced two types of snack package, which is lunch A, also called the family pack, and lunch B, the mini pack. Each pack must meet minimum nutritional standards, specifically in calories and protein. So lunch A provides 400 calories and 20 grams of proteins. Lunch B provides 600 calories and 40 grams of protein. So the minimum requirement is 4,800 calories and 320 grams of protein in total. The goal here is to find the most cost-effective combination of these two packages that satisfy the nutritional requirements while minimizing the total cost. So using linear programming, we can determine the best production plan that support efficient planning and cost control. Let's start with step 1, which is to prepare our problem for graphing. In this case, we are given two constraints related to nutrition, calories, and protein. Both are written as inequalities with greater than or equal to sign. To draw this on the graph, we must convert the inequalities into equation. So first, the calorie constraint is 400x1 plus 600x2 equal to more than 4,800. We convert it to 400x1 plus 600x2 equal to 4,800. Now, we find the intercepts to help us draw the line. If x2 is 0, then x1 equal to 12. If x1 is 0, then x2 equal to 8. Next is the protein constraint, 20x1 plus 40x2 equal to more than 320. So convert it to 20x1 plus 40x2 equal to 320. So we find the intercept for these two. If x2 is 0, then x1 equal to 16. If x1 is 0, then x2 equal to 8. This intercept help us draw both lines on the graph in the next step. Now, moving to step 2, we take the two lines we just found and draw them on the graph using the intercepts. In this step 2, we take the two constraint equations and draw them on the graph using the intercept we found in step 1. So the first line, 400x1 plus 600x2 equal to 4,800, goes through the points coordinate 12, 0 and 0, 8 with a blue line. So the second line, 20x1 plus 40x2 equal to 320, goes through coordinate 16, 0 and 0, 8 with a green line. Now, since both constraints are written with a greater than or equal to sign, the visible region is the area that is above both lines. This shaded region on the graph shows all the combinations of lunch A x1 and lunch B x2 that meet the minimum requirements for calories and protein. In other words, any point in this region represents a valid meal plan that satisfies the nutrition targets.
For the third step, the corner point of the vertices of the feasible region are identified to evaluate the potential optimal solution. To find the intersection of the point of the two constraint lines in the system of equation, simplify by dividing both equations yield the system of the 2x1 plus 3x2 equal to 24 and x1 plus 2x equal to 16. Using the elimination method, the second equation is multiplied by 2 and subtracted from the first, resulting in x2 in x squared equal to 8. Substituting this value back into the second equation yields into the x equal to 0. Therefore, the intersection is at 0.08 and additional corner points could the intercept 12, 0 and 16, 0. As we can see at my side, the equation, the first equation is 400 x1 plus 600 x2 equal to 4,800. Then we go to, and the second equation is 20 x1 plus 40 x2 equal to 320. We must divide both equations to simplify by using this 2x plus 3x2 equal to 24 and x1 plus x2 2x2 equal to 16. Using the substitution or elimination method to solve this by multiplying by the second equation, we got the 2x1 plus 4x2 equal to 32 because we multiplied by 2, or we can subtract it by 2x1 plus 4x2 bracket minus 2x1 plus 3x2 bracket equals 32 minus 24 and equally to x2 equal to 8. Then substitute the x into the x2 into the x1. You can see 2x1 2x2 equal to 16 and x1 equal to 0. Then we have these three valid corner point for each of the value. For the step 4, finally, the objective of the function is x1 plus x6 x2 is evaluate at each of these corners at points at bracket 0 and 8 bracket. The total cost of this is 148 ringgit, and at 12 0 it is also 48 ringgit, and at 16 0 the cost increased to the 64 ringgit. Thus the minimum cost of the table is RM 48 ringgit. It's achieved at both that is 0 8 and also 12 0, indicating that the school canteen may prepare either lunch A or lunch B. But the goal is not only the cost, but also the nutritional goals at the lowest cost. As you can see, the lowest cost is lunch A, but also the most nutritional, that more have nutritional is lunch B. Is a good way to, because we achieve the lunch B. That's all from me. Thank you.
Okay. For the last part is conclusion. The graphical method of linear programming provide a clear and visual way to understand optimization problem involving two variables. By plotting constraints as linear inequalities and identifying the feasible region, one can easily determine the optimal solution by evaluating the objective function at each corner point of the region. Although the method is limited to problems with only two decision variables, it is a powerful educational tool that builds intuition for more advanced techniques. It helps learners grasp the core concept of feasibility, boundedness, and optimality, which are fundamental in linear programming. For more complex problems involving more than two variables, other methods such as the simplex method or interior point method are used. That's all from us. Thank you.